Welcome to this explainer. Look, if you're a researcher or working anywhere near oncology, you already know genomic instability is a core hallmark of cancer. But today, we're breaking down a pivotal 2022 Nature paper that literally flips our understanding of cGAS STING signaling in these chromosomally unstable cancers completely on its head. We've traditionally viewed this pathway as a strict tumor suppressor, right? Well, this research reveals how highly aneuploid tumors are actually pulling off this incredible biological hijacking, co-opting the very system designed to destroy them just to survive. Here's how we're going to break this down today. First, we'll look at the cGAS STING paradox. Then, we'll map out the exact survival mechanism. Third, we'll explore a clinically actionable vulnerability. And finally, we'll wrap up by rigorously evaluating the evidence.
All right, part 1, the cGAS STING paradox.
So here is the exact paradox the researchers set out to solve. We all know chromosomal instability, or CIN, generates micronuclei. And when those micronuclei rupture, they spill double-stranded DNA straight into the cytosol. That acts as a massive, blaring alarm bell for the cGAS STING innate immune pathway. Normally, that triggers apoptosis and flags the cell for immune destruction. So logically, if this pathway is so lethal to a tumor, why don't these highly aneuploid CIN-positive tumors just mutate it? Why do they keep the alarm bell intact? This paper forces a complete conceptual shift. Under the old paradigm, we thought of cGAS STING strictly as a tumor suppressor, something that induces cell death and innate immune responses. But this new paradigm, it reveals a wild twist. Instead of acting solely as an anti-tumor mechanism, cGAS STING is actually being utilized by CIN-positive cells as a necessary lifeline. It's functioning as a pro-survival adaptation, basically allowing these highly mutated cells to tolerate chronic genomic stress that would otherwise absolutely destroy them. Moving on to part 2, mapping the survival mechanism. So, how exactly does this hijacking work? The researchers didn't just look for correlative markers. They mapped the cascade step by step. By inducing chromosomal instability using MPS1 and WE1 inhibitors, they tracked the whole sequence. It starts with CIN, which leads to that micronuclei rupture, predictably activating cGIS and STING. But then, instead of inducing cell death, the signaling pivots. It triggers massive IL-6 production, which in turn drives STAT3 activation, and ultimately, that guarantees the cancer cell's survival. To prove this wasn't just a coincidence, they brought in CRISPR. They genetically ablated either cGAS or STING in these CIN-positive cancer models. And when they did, they didn't just see a slight dip in growth. They observed massively reduced viability and a huge spike in apoptosis. The CIN-driven cancer cells practically collapsed. This is your proof of causality. The intact cGAS STING pathway isn't suppressing the tumor, it's an absolute requirement for the survival of these genomically chaotic cells. What's fascinating is how this study exquisitely dissects the competing downstream branches of this pathway. It's basically a biological fork in the road. On one side, you have the pro-death branch, mediated by STAT1 and the ASK1 JNK stress signaling pathways. On the other side, the pro-survival branch relies on IL-6, STAT3, and non-canonical NF-kappa B signaling, specifically REL-B, to protect the cell. They showed that if you lose STAT3, it mimics a cGAS knockout and the cell dies. But if you remove STAT1, you actually rescue the cell and enhance its survival. It's this intricate balancing act, and the tumor entirely tips the scales towards STAT3. Now, this right here is the aha moment of the paper. To absolutely cement IL-6 as the central mediator, they ran a rescue experiment. They took cGS-deficient cancer cells that were actively dying from severe chromosomal instability, and they just added recombinant IL-6 back into the mix. The result? Survival was fully restored. It's unequivocally the mechanistic linchpin, proving IL-6 is the downstream cytokine absolutely necessary for CIN tolerance. Which brings us to part 3. A clinically actionable vulnerability. The researchers realized something huge. If the tumor is this dependent on IL-6, we already have a tool to exploit that dependency. Enter tocilizumab. As many of you know, this is an FDA-approved monoclonal antibody that competitively inhibits the IL-6 receptor. It's a drug sitting right there in the clinic, traditionally used for autoimmune conditions like rheumatoid arthritis. They hypothesized this could be the exact weapon needed to sever the tumor's lifeline. And honestly, the results were striking. Applying tocilizumab selectively and severely impaired the growth of CN-high cancer cells, while barely touching CN-low or normal cells like MCF10A. That selective toxicity is a massive translational strength.
It tells us we might be able to induce a catastrophic collapse in highly aneuploid tumor cells without causing widespread, indiscriminate damage to a patient's healthy tissue.
To make sure this wasn't just some artifact of a single lucky cell line, they put this through the ringer. The robustness of this selective targeting was validated across an incredibly diverse array of models: triple-negative breast cancer, lung, ovarian, melanoma, and leukemia models. They used both acute and chronic CIN induction in human and mouse cell lines, and crucially, they proved it in vivo, significantly delaying tumor growth in mouse xenograft and immunocompetent syngeneic models.
All right, let's wrap this up with part 4, evaluating the evidence.
We have to be objective here and look at both sides. The strengths of this study are undeniable. The broad validation across multiple cancer types, leveraging an already FDA-approved drug, and establishing rock-solid causality through CRISPR. But we do have to acknowledge the limitations. There's a heavy reliance on artificially engineered CIN waddles like DNMCK overexpression, which might not perfectly mirror the slow, natural evolution of human tumors. Plus, the animal models used relatively short treatment windows. What about long-term resistance? We just don't know yet. And finally, we can't ignore the potential risks of broadly suppressing IL-6 and what that systemic immunosuppression might do in a real human patient.
But to bring it back to human reality, the authors did look at clinical data. By analyzing the cancer genome atlas, they confirmed that highly aneuploid tumors with elevated cGAS, IL-6, and STAT3 activity directly correlate with worse overall survival outcomes in human patients. Now, sure, it's observational, but this transcriptomic data firmly aligns with their preclinical models. It shows this pro-survival axis is absolutely driving aggressive disease out there in the real world.
So where do we go from here? The scientific community has some clear marching orders. We obviously need human clinical trials to determine tocilizumab's real-world efficacy in oncology. But we also really need to untangle the immune complexities of IL-6 blockade. Does it ultimately help or hinder anti-tumor immunity long-term? We also need to discover and validate predictive biomarkers, like the Sin70 signature, so we know exactly which patients are actually going to respond to this therapy.
I'll leave you with this profound closing thought. This study boldly reframes genomic instability. It's no longer just a bad omen or a biomarker of an aggressive, hard-to-treat cancer. It is a targetable, fundamental biological dependency. By mapping the survival cascade from cGAS staying straight down to IL-6, it really makes you wonder, has the key to collapsing our most chaotic, chromosomally unstable tumors just been sitting quietly on the pharmacy shelf all along? Thank you so much for joining me for this explainer, and I highly encourage you to read the full Nature paper to dive even deeper into the data.